Move on to the last talk of the day before we have our roundtable Q&A. And so it's my pleasure to introduce to you guys. I've been trying to pronounce the surname correctly for the last 6 years and failed. Anna Blazejewska. The closest.
Yeah, I think that's the best so far,
yeah. So Anna is an assistant professor at the NMGH. She was a former postdoc of John. And one of the people that I love the most from Anna is the intercortical smoothing, which is really useful for our layer segmentation. We use different heuristics and different types of smoothing kernel to remain faithful to the layer architecture while still performing smoothing within layers. We'll probably see something about that tomorrow. Soon?
Today?
Even better. Okay. And Anna is one of the pioneers of the Freesurfer pipeline. And so she's going to be showing us some of our Freesurfer pipeline today, and then tomorrow she's going to show some of the hands-on tutorials. So I'll leave the floor to you. Thank you so much, Anna.
All right. Thanks, Luca, for a nice introduction, and thank you all for having me here. So just to clarify, I'm not a Freesurfer developer, I'm not even part of Freesurfer group per se. I'm just a user, and I'm going to be presenting a pipeline that we optimized to use for our experiment with the laminar fMRI. Now, this is kind of a little bit off-label use of Freesurfer because it's originally been developed for the 3 Tesla 1 millimeter data. So, and for that kind of data, it works perfect out of the box. But for this high-resolution data from 7T, we do a few tweaks that I'll also show you to make it work better. And one more clarification to start off. We are a little bit conservative. We are right now working on version 7.4, so that's what we're going to be using tomorrow. These results that we're showing today are from 7.1. They're relatively similar. But there's already Freesurfer 8 out there, and there's a lot of updates that has been done in the last few years, mainly using some deep learning methods that I'm going to quickly go over. We haven't really tested these methods to the extent that I would trust to use them on our data. But we are definitely planning to, and we are hopeful that maybe some of the, especially manual interventions and corrections that we are doing can be eliminated through that. Okay, so just to get out of the way some assumptions that I make here. So this pipeline I will be showing is for single subject analysis, and as I said, for sub-millimeter resolution data acquired at 7 Tesla. And we're going to split it into 2 parts, similar to previous presentations, to anatomical data processing and functional data processing. Anatomical data will be processed for surface reconstruction. I'm going to talk briefly about acquisition that we decided to use to make this processing even easier. I'm going to talk a bit about the bias field correction and tissue segmentation, surface reconstruction, which is the main part that Freesurfer helps us with, and this tweaks that we've made for our high-resolution data, namely edits of the segmentation and also a high-res stream. And finally, I'm going to show you how we create a family of surfaces across cortical depth to create this sort of coordinate system that we can then perform our analysis on. And I'm only going to talk about the functional data. So we're going to look at this laminar level functional activations. I'm going to just briefly mention pre-processing. A lot has been said already about it today. I'm going to talk a bit about the registration and then projection of the volume data onto surfaces. And I'm going to show us this previously mentioned anatomically informed smoothing as well that we've developed a few years ago with John. And finally, I'm going to just add a little bit on the future directions. As I mentioned, the Freesurfer is under constant development, so there's a lot of new things coming to life that we want to test and perhaps use as well in the future. And at the bottom here, you have just 2 sort of critical papers that have been published that sort of describe the surface reconstruction, the foundations of this whole method. So if you need any more details on like actual methodological aspects and maths and that, you can read these papers. Okay, so let's start with the anatomical data. And as I said, I'm going to say a few words about acquisition. There are different acquisitions that people use. There's a lot of people that use MP2RAGE. We decided to use MP-RAGE, which is the magnetization prepared T1 weighted image. We like it because it has strong tissue contrast, and it also allows us to get relatively high resolution in the reasonable imaging time, which means 7-ish minutes. But unlike the data we're going to be working on tomorrow, we actually use multi-echo version of it. So This is the version with 4 echoes. We've got 4 different images with slightly different contrast, and we choose to use this because it helps us to partially suppress dura. So dura, which is the tissue around the cortex, as you can see, tends to have similar intensity and sometimes gets into our segmentation of the cortex, and that can screw up the precision of the PL surface placement. So this is just a little help with that on the acquisition level. We combine those to increase SNR. And just to address a couple of other sort of acquisition level things, these magnetization preparation methods, they are a little problematic when we have to deal with the RF field inhomogeneity at 70. And so we also use the sequence with the special fancy pulses that are optimized to minimize these effects. So this is just trying to get the best data we can for a given pipeline that we're going to run on them. Now, to go a little bit more on this inhomogeneity, this is something that is basically due to the properties of the tissue. It can be to some extent modified by transmit coil design or coil geometry. And in general, it results in spatially varying transmit efficiency across the image and varying flip angles that will affect our excitation pulses. And in the actual image, we'll see it as a bias field, which is a smoothly varying intensity bias, and also degraded contrast in the regions where the inhomogeneity is high. And it can be a big challenge for the segmentation and therefore surface reconstruction, because the algorithm will not always be able to tell if the intensity change is because of the tissues being different or just bias being sort of added to that difference. And conventional correction methods, including ANTs that are used in Freesurfer, fit low-order special trends to fix that. And this is just not complex enough for the 70. So what we do instead, before we feed our data to Freesurfer, we apply SPM to perform joint estimation of bias and tissue segmentation. And this is just an example of how the data looks before with some visible bias and after. But nothing is this simple, so there are certain trade-offs in applying SPM. So as I said, it does two things in the same time. It tries to mitigate the bias, and it also tries to segment the tissue and preserve the contrast in this tissue. And so this is work by Daniel Gomez, John's former postdoc here. Daniel actually looked into different parameters and if we could optimize them for our specific 7T data. And there are 2 parameters that were crucial for that. That's bias regularization and bias smoothness. Now, if you can see these 4 images here at the bottom row, we have the bias smoothness of 60. I believe that's the lowest value that is accessible through the graphical interface. So if you want to make it lower than that, you have to use scripting. But that's not important. What's important is that you can see that these images don't look very good, and I would not want to see the surface reconstruction from them. In the top row, things look a little bit better. And this is the particular combination that Daniel found was the best for surface placement, for surface reconstruction and precise surface placement. And this is just an example. I'm not sure which surfaces are which here, but this is the kind of offsets that you may get just by getting the bias field correction slightly off. And this is an amazing sentence that Daniel found in the SPM manual that I'm just bringing up here. So basically, if you use a different acquisition, you might want to review these parameters again and make sure that they're still working. It's never set for good forever. So it's always a good idea to sort of be aware of this. If you're seeing some errors in the surfaces, maybe you have to go back and check your bias field correction. You may also go back and acquire different data, but that's more difficult. So this is just sort of to keep in mind that these things can be optimized. And sort of a byproduct of it's part of the SPM bias field correction and tissue segmentation is tissue segmentation. We treat it more as a byproduct, I guess. And so we have these 5 tissue classes that are produced in the form of the probabilistic maps. It's a gray matter, white matter, CSF, but there are also 2 more, soft tissue and bone. They're all produced based on the Gaussian mixture model. But what's helpful or useful for us here is that we can use these last 2 classes, the bone and the soft tissue, to potentially help with cleaning up some of the Freesurfer segmentations, and I will show you an example in a few slides. Can I move this thing somehow? So
Just click on the X.
X? On that X. I don't see it on my screen. It's not on my screen. Yeah, I don't think I can. I don't think I can put the cursor on it.
You're behind it.
Yeah, I'm behind it. See, it disappears.
People can move that.
I mean, I just think that titles are, you know.
Volume.
No, I have to extend. Okay, I just saw magic. All right, thanks, Renzo. So, okay, so now I just want to actually start talking about the Freesurfer part of this Freesurfer pipeline, namely Recon-All. And I know there's, from previous discussions, seems like a lot of people here at least know about Freesurfer or used it before or are proficient users. So these people will be bored for the next 3 slides, but I just want to make sure we all have sort of the same, you know, baseline information about it. So that's not working. Oh my God. Okay, so there are 2 sort of streams or parts of Freesurfer surface reconstruction, the Recon-All, volume-based part and surface-based part. And they sort of occur consecutively, so we start with the volume-based part. In the volume-based part, we first start with intensity, correction, and normalization of the input volume. And as an output, we get this T1 MGZ volume. MGZ is native format of Freesurfer, and it's very easy to convert to and from Nifty using MRI convert, which is also part of Freesurfer. And what's also important is that every time we run Recon-All, we create this structure of directories, and it's always the same. And certain outputs land in certain directories. So once you learn it once, you always know where to look for the different files for a new subject. And this volume-based stream outputs happen to land in the MRI directory. The second step is brain segmentation. Automatic subcortical labeling, we're not going to talk too much about it, but just to mention it. And finally, white matter segmentation or creation of this inside cortex mask, which includes white matter and ventricles. And this is an important volume because this is what is being used sort of for transition from the volume-based to surface-based stream. So, in fact, this transition happens by first covering this white matter volume with triangles to create a mesh, which is called tessellation. And you can see here on the left we have like a surface version of it. On the right we have a meshy version of it. And from now on, everything that is done in this stream is done separately on the left and right hemisphere. But if you look closely on the surfaces and you zoom on them, they're sort of rough and jagged and don't look all that good. So the first step of the surface-based stream is in fact refining the surfaces. So basically what is being done is adjusting the placement of the surfaces, adjusting placement of vertices with smoothness constraint, but following the T1 intensity gradient. And that creates our left and right white matter surfaces. And by the way, all the surfaces end in the surf directory. And subsequently, from this white matter surface, we create, again by expansion following T1 intensity gradients, PL surfaces. They'll look like this. So these are the 2 main surfaces that define our cortical ribbon, so kind of the most important to us. But in this process, a few other interesting constructs are being created, such as inflated surfaces, which are created by inflating, further expanding the surface with distortion constraints, but with no intensity constraints. And that looks like this. This is a useful construct for sort of visualizations, and you'll see it a lot in the stock. And if we inflate even more, we'll go all the way to the sphere. And sphere in the process is also helpful for fixing topological errors. So basically expand, then we can detect and correct these errors easier, and then we can sort of deflate it back. It's also used for registration across subjects. That's not something we'll be talking about today, but it's also good to know. Okay, so one thing that has been said already a few times here in different contexts, Freesurfer surfaces are the kind of surfaces that we have the same number of vertices across all of them, and we have correspondence across like between these vertices. So basically, a vertex on the PL surface will have a corresponding one on the white matter, and also on the sphere or on the inflated surface. And this is something that's going to come up in a few different places here. And now I just wanted to quickly introduce the concept of surface overlay. So surface overlay is sort of a data file that basically has a value assigned to each vertex. And two interesting and useful overlays that are created in Freesurfer that can sort of illustrate that concept as well is a cortical thickness overlay, which is the distance calculated between the white matter and PL surface. And you can see how it looks like overlaid on this inflated surface. And similarly, cortical curvature, again, overlaid on the surface. But you can basically use this overlay to represent any other types of data, like we'll be creating in a few slides overlays of the functional data that will be also projected on the surfaces. Okay, so as any good software package, Freesurfer also has a viewer, and that viewer is called Freeview. And obviously has a graphical interface, but it can also be called from command line to look at the volumes in the Freesurfer format at surfaces. And you can specify all sorts of parameters, as you can see here, the edge color, for example. And you can also load overlays, like you can see here, that overlays always correspond to the surface because they're assigned to the vertices on that surface. And this is the useful command to learn more about the different flags and parameters that you can pass to Freeview. It's a really cool tool if you want to, for example, automatically generate a lot of screenshots for a movie. You can basically set it up in a loop and it will run there, or across the subjects with the exact same positioning. So it's just a pretty neat thing to use and make things it's much easier. And this is just a quick, in preparation for tomorrow, I hope it's gonna work. It's a demo of the Freeview, and the main thing I wanted to show you is how to load the overlay, because this is not the most intuitive thing when you get started. But we're loading a volume. You can look at the different views. Again, this is pretty basic, but I just want to make sure that everyone knows how to do it tomorrow. You can load the surface, PL surface, right hemisphere. So you can see the outline of the surface. You can change the color. And you can also load. Okay. So this is just looking at the surface in 3D view. And you can also load inflated surface for the other hemisphere. And if you want to go, you can change the visualization. Should speed it up a little. And here we go. We will load, I believe, the cortical thickness overlay. So this is how it works. It's basically a file that contains numbers that are being assigned to the list of vertices that is included in the surface. It's pretty straightforward, easy to operate in MATLAB as well. And we can change the thresholding. Okay, I'm gonna move on because it's taking forever. Next one. Okay, so a few other things that is good to know about the outcomes of the recall. There's a whole directory of labels that are atlas-based but are subject-specific. We are obviously mostly interested in the visual cortex label, but some other people may be interested in different regions. There's also a directory of scripts where all the log files and all the commands that are being run end up. So if anything goes wrong, this is where you can start debugging, you can check the versions of the things you run. It's just good to know that all these things are being saved. To learn more, you can go to a really good wiki page. You can also try asking experts from the mailing list. This is a package that is under constant development. It has a lot of different sub-programs, so there's a lot going on, and this way you can potentially reach to actual authors of these tools and ask them direct questions. There's also a recon all page of the wiki that may be helpful tomorrow. And there's also this table that I find very useful that lists all the tools, inputs, outputs, and flags that are used in recon all. Now, this is valid for version 7.4. For version 8, it's not, because a lot of the tools changed. So this is something we're going to be using tomorrow, but for future reference, this is not. If you're using the newer version of Freesurfer, you probably won't find there the things that you need. There's also a nice tutorial for Freeview if someone wants to see more videos. And there's also a nice tutorial for troubleshooting of the data. And I actually stole 2 videos from them that I'm going to show you in a second that will illustrate how we can correct problems that we often see in our high-resolution data, which is misplacement of PL surface and white matter surface, which are due to the errors in the segmentation that has also been talked about quite a bit in the break. Okay, so let's start with the brain segmentation. Again, this is the old version of the brain segmentation. Right now, a new machine learning, deep learning approach has been developed, but we are still using this, so I'm gonna address the issues that we still have with this approach. So this is the MRI watershed command. And what often happens is that the brain mask that we're getting includes sagittal sinus or dura, and that can lead to the PL surfaces being misplaced. So here is an example of the mask that is just a little too big. And this is again work by Daniel, who was trying to optimize it. So you can see that's the problem. And the first order approach is to change the parameters of the MRI watershed. So we can, for example, change this H parameter. That's I believe a pre-flooding height. And as you see, when we modify this parameter, we are getting better results here on the back of the head. It actually looks pretty nice now. But this is true on the back of the head, it's not true in the whole brain. So the problem is that these parameters are global, and the intensities of the tissues are not necessarily global. So you can see that here at the top of the head, it actually started to eat the brain. So that's not good. So the other potential thing that we could do, I mentioned before that we'll be using this SPM tissue classes. So this is an example from our data. You can again see that there's a bit of a problem with dura being included in the mask and in the surface. So what we try to do sometimes, and it actually does work well sometimes, we take the SPM bone and soft tissue segmentations, threshold them because there are probability maps, and we create this no brain mask that is trying to basically we basically subtract it from the brain mask. We're trying to remove those regions that we don't want to see them. Unfortunately, in this case, it didn't help much. You could say that, sure, I mean, we could change the threshold maybe. These are probability tissue labels, tissue maps, so we can just, binarize them with different threshold. But it's also kind of becoming clear that if we start making this mask too aggressive, we may actually again lose some brain in the other regions. So the third last resort approach is to perform manual corrections. So basically, if we look at this zoomed in region here, our corrected mask would look like this. And then we would just recreate the PL surface to make sure that it worked, and it did. And here is the video from the Freesurfer website, again showing how to do that in Freeview. They're actually looking at the different region, but this is just, again, the demonstration. If someone wants to do it at home, we won't be doing any manual segmentations tomorrow, but if you want to work on your actual data, it's just, it's pretty straightforward. You do want to make sure that you look at all 3 planes, not just in this one in which you're drawing, because you may get this like soul patterns. But it's basically just removing part of this mask. Now, what's important here, in both cases, the brain mask, and also you'll see that soon in the white matter correction, we're actually correcting segmentations, and then we are letting Freesurfer to change the placement of the surface. So it's sort of like a not direct approach of moving things around. Okay. So now let's talk about the white matter segmentation. Again, this is a Freesurfer command, recon all command that segments white matter. And again, here the problem is that this mask often includes some of the gray matter. They can also be holes potentially, but I would say from experience we're seeing more of the gray matter actually being part of this mask, and that will cause the white surface to be misplaced. And this is an example. You can see a problem area. So again, we can try to fine-tune this approach. This is again work by Daniel. And what we can do, we can try to pass and change the thresholds, lower and higher thresholds for white matter and gray matter to this program. So you can see that it did improve a little bit. There's still some issue remaining, but it kind of does look better. Now, I'm not showing it here, but very likely it will cause similar issue like as about brain segmentation, that basically will improve things in one location and not necessarily in some others. And this is because the mean intensity of gray matter across different brain regions varies. So you can optimize things in one location, but not for the whole brain. And this is just an example, again, plotted by Daniel. You can see in these histograms that if we look at the whole gray matter with the same threshold, that's the red line, as in just Cochrane in this orange histogram, we'll get very different results. So this is kind of a difficult problem to solve just by setting these global thresholds, right? So if we cannot set the thresholds, if we cannot solve it manually, we go to our manual approach. So again, you can see there's a little bit of a sticking out white matter, and you can also see that the surface is sort of following the segmentation, so it is a segmentation error, it's not something else. And again, we can edit it and run the parts of Reconol that will regenerate the surface and also run some further steps, and it will be improved. I'm not sure how visible this is, but the yellow one is the improved one. And again, I have a quick video. It's pretty self-explanatory, so I'm just gonna, here they have a hole, so they're gonna patch the hole. So basically, once you create this mask, you probably want to back up your old mask just in case in the Freesurfer Reconol directory. You replace this with this new mask, and then you rerun the parts of Freesurfer. All the information regarding what labels to pass to Reconol to run just parts of the pipeline, also in this table where all the different commands are listed. Okay, that was drawing. And finally, perhaps the most important upgrade or change to the Reconol that we make to process our high-resolution data, and that is using so-called high-res stream. That is something that Natalia developed with John a few years back, and it basically comes down to passing the flags to the Reconol that will sort of modify the way it works. High-res flag, which will stop the Reconol from downsampling our input images to 1 millimeter, which is what it naturally does because it works the best on that kind of data. And also the expert flag with the expert file, which will increase the number of iterations of surface inflations that are being done. And this is important because with the high resolution data, they will produce the meshes with higher vertex density. And so we need more iteration in order to inflate the surface to the sphere, correct for the defects, and come back. And if you don't do it, you will see kind of wiggles on the surfaces. I don't have a picture, but you will know once you see one. All right, so finally, I want to move on to show you how to create this family of surface meshes to have the surface-based coordinate system with MRI's Expand. So we're trying to create evenly spaced surface meshes like this. So this is our white matter and PL surface, and these are our meshes. You can pick how many of them you want to create. This is an example with 9 intermediate surfaces because we end up having nice 10 layers. And you can appreciate on the zoomed in example, color-coded, how they look like. And again, just to bring it up, this is a family of surfaces, and each of these vertices has like a brother in the neighboring surface, because all of these surface meshes will have the same number of vertices. And the topological correspondence between them is what helps us do certain types of analysis, as it's been discussed, and I'll also show that in a few slides. Okay, so with that, I want to switch and talk more now about the functional data and the laminar level activations. A lot has been said about pre-processing today, so I'm just gonna make it very quick. In general, we're working on the 4D data, and what we're trying to do is to ensure that this data meets the assumptions that are made by analysis, such as that the time courses come from the same anatomical location, or that the voxels in a given time frame were sampled in the same instance, or that there is no warping and distortion to the images. Some people also do smoothing, but we'll talk about smoothing more. Some people hate smoothing. We actually don't do smoothing, but it can be helpful sometimes. Now there's a question in what order to do these operations that may not be having just one answer, and then there is also interpolation problem that has also been discussed a lot, so I'm not going to go into details on that, but it's important to keep all these things in mind. What I'm going to talk a little bit more about is registration, and Rainer actually did a really nice overview and explained it so well that I can probably go pretty quickly through the slides, but the registration we use in Freesurfer is the BB register by DAGRIP, and it's, as we know, boundary-based registration. Here is sort of a more mathematical version of the nice figures that Rainer showed. I'm not going to go into details on that. What we said was that it uses boundary-based const function, and Rainer also explained what this is. And now what we like about it is that it's actually based on local tissue contrast, and that makes it robust to slowly varying biases, so that's important to us. In general, it's inter-subject, but cross-model registration, and as we also have seen, it's very robust for aligning partial volumes to the whole brain, which, again, I think it's been said, I have a very difficult task because everything interesting has been said already, but I think it's been said that once we push for the high resolution, these volumes will likely become smaller and more trickier to register. So in general, it's great for laminar fMRI studies. And there's a few extra tweaks that we can do with BB register to make it work even better that we sort of routinely do in most of our laminar analysis. Number one is to initialize it with some kind of initialization. I mean, you can initialize it from the header, and in many cases it works, but you can also just open the volume and the surface in this little viewer and basically try to align it, try to make a best guess manually. Normally, if the data is acquired sort of in the same session, it would, and if there was not too much motion, if there's a lot of motion, you may not want to analyze the data anyway. But if there's not too much motion, you can probably do it in like a minute. I usually wouldn't spend more on that. But it just helps to make it extra robust. You can also obviously try to skip this step and see how it works and add it if you want to. Now for the data for tomorrow, it was especially extra difficult task because the anatomical data I was working on at least were acquired in a different session. So I actually prepared the initialization matrix for you because it was just so far off that it took a minute to get in the correct place. But anyway, this is just the way how we would do it. And another trick that we can do, we can use the label to mask out the distorted regions for the registration. So if this is a concern, we can basically use this mask, which is based on the Freesurfer labels, and these regions will not be taken into account in the registration. So this is the flag that can do that. And apparently, as I learned from that, we can also pass the voxel shift map to BB register and actually include distortion correction in registration. I haven't tried it myself, but what it does, it actually warps the surfaces to match your fMRI volume data. Now it will all depend on how accurate and how good your voxel shift map. So there are some questions there, but that's just an alternative if someone wanted to actually apply it. Okay, so the next step, once we figured out this registration and our functional data is theoretically aligned to the anatomical data, just to clarify, we are not really aligning fMRI data and interpolating them. What we are doing, we are creating a transformation that can be then used to project this data onto the surfaces. So obviously we'll generate like a volume that we can look at and make sure that this registration worked just for sanity check. But in general, what we do, we apply these transformations to project data on the surfaces. And this is to enable the surface-based approach, where we're basically having this family of surfaces that we already discussed, and we're creating surface overlays that we can then display on these surfaces, where we, again, as we did previously with the thickness or curvature, creating by assigning voxel values to surface vertices. Okay, so if this is our cortex, and this is our voxel grid, we'll take this one blue voxel, and we'll assign the value of this voxel to the two surfaces, three vertices in this case. And this is a cool method for visualizing the surface tangential activation patterns as a function of cortical depth. Thanks to this topological correspondence that has been also talked about, it's actually easy to generate profiles in specific locations, not inside larger regions of interest. But it does give issue with counting voxels, and that has been discussed already, that depending on what kind of analysis you're doing, you may want to choose different way of creating surfaces or working either in volume or surface space. So this is just another tool that I'm sort of proposing here, not really any better or worse than the other ones. What's also interesting, and we should keep that in mind, is that with this super high resolution data, like some people are acquiring at 10 plus T, we actually need to pay attention to our density of the meshes, because it may happen that our meshes will be too sparse and we'll have to upsample them in order not to lose some voxels in this process. Okay, so this is an example of this is actually the API data. It's just color coded in a weird way, overlaid on the white matter surface from Freesurfer, and here we go over different surfaces all the way to PL surface. What's important to keep in mind, so we can obviously project this fMRI data that we aligned with the anatomical data, but we can also use the same transformations to project anything. Labels or regions of interest that we created in the volume space, statistical maps that we calculated in the volume space, you name it. Anything that was in the same space as the PI can be converted. And what I also wanted to point out that maybe has not been, so John showed it in his talk today, but maybe not everyone realizes that we can also perform voxel-based analysis. We can basically take these two surfaces and the transformation and go back and calculate the depth for each voxel and proceed with the voxel-based analysis. So this is just to clarify that this is not the only way we can do analysis in this framework. Okay, so now I'm going to talk a little bit about smoothing, and again, smoothing has been mentioned, I personally don't smooth my data. However, there are some people who do, and there are good reasons to smooth. And one reason is to increase SNR and detection sensitivity. In case you are running group analysis or not single subject analysis, this may also be helpful for removing across subject variability. And it can also be helpful to remove false positives because the activation is assumed to be smooth. But traditionally, in the conventional MRI, conventional fMRI, the kernels that are being applied are these 3D Gaussian kernels that will average over everything, such as different types of tissues, voxels from different opposite banks of sulcus, and potentially different functional areas, and will just mislocalize the activation and cause a huge mess. So basically we try to reduce the errors, but we actually introduce more errors. So because of that, for those who want to smooth, surface-based approaches have been proposed that restrict smoothing to the cortical ribbon. So it's not going to mix all these different tissues. And what we proposed was sort of a variant of this kind of surface-based smoothing, but with the extra feature that we're actually now using the submillimeter voxels to look at the cortex as a 3D structure. So instead of talking about ribbons are flat, we're talking about the 3D cortex. So if this is our cortex, we'll take the small voxels and redistribute them. And that can help, at least for conventional studies, to avoid signals originating from CSF in white matter, because we don't want the noise and we don't want the white matter where we don't expect to see activation. So we can weight the contribution of these different voxels and smooth like this. This is obviously similar to Renzo's smoothing from Laney as well, but what we can actually do here which we thought was cool. We can create the kernels that they're not only just following the folds of the cortex, but can also be adjusted and parameterized both in tangential and radial direction. So for conventional studies, again, that would mean that we are trying to increase sensitivity and specificity of the fMRI measurements. And we found that this kind of kernel, no surprise here, that sort of avoids the white matter and PL surface is actually the best for that. And we also tested that on both resting state and task data. Comparing to volume-based smoothing, again, not so much surprise here. It performed better both in terms of sensitivity and specificity, but it also performed better than the larger voxel non-smooth data. So, like you can see here in this plot. So we found this kernel that has the best balance between this specificity and sensitivity, which is cool. So basically, if you see anyone trying to acquire low-resolution data, you should tell them to stop, because it would be much better if they acquired high-resolution data and then smooth them with our method. But what does it really mean for the laminar fMRI people? I mean, we don't really care about this, we are not acquiring 3 millimeter voxels like ever. Well, so as it's been said, it can be useful when we have the prior information about the spatial structure of the activation. Now, again, I'm not talking here about doing analysis on the smooth data, but it does help to see things. It does help to sometimes just make sense out of the noisy data we are looking at. And as John also highlighted, as long as you still have the non-smooth data on the side, there's really nothing wrong with aiding your visualization a little bit. It can also help, in my opinion, to create ROIs from, for example, a separate functional localizer scan, which will be then more smooth and won't have holes like you would have just by thresholding. And in general, it can aid the visualization of the results. So as much as you kind of have to be careful with any smoothing, even cool smoothing like ours, you still can use it for certain applications. Okay, and finally, I think we got to what everyone was waiting for, the actual activations, laminar activations. So I'm just going to show you a simple example of how you can do it in this framework. There's a lot more you could do, obviously, but one simple way to look at the activations in this family of surfaces-based framework is to just calculate your maps across all of your runs in volume space with whatever tool you like. I actually used the feed from FSL here, and project it on the surfaces. So this is just the output from feed. It seems like it worked. There's activation, the visual cortex roughly. And this is how this activation actually measured at the mid depth would look like on the inflated surfaces. So what I'm doing here, I'm looking at the mid depths, but I'm projecting on the inflated surfaces. Again, the topological correspondence allows me to do it. And this is activation from one run. But what we can do, because we have all this fMRI data, we have transformations for them to the anatomical space. We can actually project all of the statistics acquired in this volume space and average them. And this is the average over 10 runs. It's kind of, I didn't clean it up or anything. It's just really to show you how this works. And this is a smooth version, by the way, with just very, very tiny bit of smoothing. Okay, so I run really fast through that, but I'm almost at the end of this presentation. I just wanted to talk a little bit about these future directions that I have mentioned a few times throughout the talk. So the new version of Freesurfer, as I said, has new deep learning tools in it. There's SynStrip for brain segmentation that is supposed to work on any kind of brain image, and we did test it quickly on some of our data, n = 2. Seems to work well. But honestly, I think it looks promising. It's said to be more robust. It's automatic, and it also, according to Doug that I've been emailing with, it actually is supposed to solve our, well, not sure if ours, but it's supposed to address the sinus and dura problems. So I'm actually curious to see how well this will work on the high resolution data. I don't believe it's been tested extensively, at least, or I'm not sure if it was trained with the 7T data or sub-millimeter data, but we're in the process of figuring it out. So we're trying to upgrade our pipeline. The second new development is SynSec, which is a segmentation tool, and again, it's promised to be more accurate and deal better with tissue segmentation. We haven't tried it yet, but we are planning to. And this is just to mention for complete picture. There's also a nonlinear registration method for registration template. This is not really part of Recon-All, but it's also one of the new developments in Freesurfer. I believe there are also segmentations that can somehow deal with the white matter lesions and also with extracerebral structures. I again haven't tried those, or with like ex vivo smaller pieces. So anyway, there's a lot of development there. And these methods are supposed to be, as I said, more robust, but also faster, like significantly faster. And that I can confirm. The Recon-All with the new upgrades is much faster. They also are supposed to be acquisition and contrast independent, which is really interesting because if that would work for our data, that could help us solve some of these issues that everyone is acquiring different anatomical data. Maybe there's not going to be as much difference here as it is right now. But as I said, systematic testing is necessary. However, if it could help us to at least partially reduce, if not eliminate, that's mostly my hope, this manual edits that we have to do, that will be still a huge step. And just to show you at the very end, this is a completely different topic, and these are, well, not completely, but these are results that I just got from Ola. This was presented at HPM last year. And this is the ex vivo based work on automatic prediction of infra-supragranular border. As you can see here, the zoomed in version. And sure, this is ex vivo data, but you can see that there is interest. There's interest in looking into this cortical layers, and I know that they're also trying to test it on the in vivo data. So there is more developments going on than in the direction of this high resolution and laminar analysis. So these are some results that we generated in the surface-based Freesurfer framework a few years back with John. And I wanted to thank Jack and Bruce, who made Freesurfer and are developing it, John, who taught me everything, and Daniel for contributing the slides, and all of you for your attention.
Questions? Last one.
Maybe.
So this high-res thing, you mentioned that it kind of modifies how things work. What do you mean by that? Or why are we not doing like this for everything? But like for low resolution as well? Or is there a price we pay when doing it?
So as far as I know, I think John probably knows more because he has developed that, but it basically just stops Freesurfer. So normally when you input the data, there's sub-millimeter resolution to Freesurfer, it would automatically, as first step, down sub-bundle to 1 millimeter because that's what it works on. And we don't want to do that if we have like 0.75 MPH. So that's it. It doesn't really do, so that's for the high-res plaque. Then there's the inflation that I was trying to explain on the basically increasing the number of inflations of the surface when you're creating a PL surface so that it can actually be properly fixed, because I think the default number is like 10 or something, and if you have much more dense mesh, you need more to go further. But these are like 2 separate flags, so these are pretty small changes.
So if I would just make my standard pipeline of Recon-All high-res with the number of iterations, I might have had a slightly larger data size, but that's the price to pay.
I'm not sure if would the data files actually be larger? It would take longer, potentially.
Yeah, you skip the conforming step. Yeah, so there's this step, the first step they call it conforming, no matter what your voxel size is, position, it would conform it to one another and generate the surfaces.
The whole benefit of that is to be faster.
Actually, it's a historical kind of artifact. I think that when they first developed it, they were working with sometimes anisotropic data, like 1 by 1 by 1 by 1, and so they would.
That's the error right there. right there.
Yeah, well, again, the thing I think Freesurfer is really remarkable because it works on such a huge variety of data. I think you're going to give them credit for this. It's like pretty robust. And so, yeah, so I think they just conventionally would always conform to 1 millimeter. And because everything was, always with 1 millimeter voxels, deep in the code, they didn't really distinguish between millimeter units and voxel units. It was just between one. And so it's actually a lot of work, to be able to adapt Freesurfer work from sub-millimeter voxel sizes. But to answer your question, I think there's no penalty. Yes, your meshes will have more elements because if you generate your meshes with margin cubes, which is the initial step, smaller voxels, you're going to get more vertices, some files, will be bigger, everything will take up more disk space, things will be a little slower.
But if you input 1 millimeter data with a high-res flag, that wouldn't change anything, right? So that's kind of what I meant.
Yeah.
So if you set it up like this, but then still want to work on 1 millimeter data, it shouldn't be any change. So you can basically just always use it like that, just in case.
No real downside, always specify.
So the inflation, if I might follow up, there's a mesh subdivide, right, to have a higher density, vertex density.
Yeah,
That's for upsampling, yeah. But
It's not the inflation, it's a different thing.
That's upsampling. I believe so.
Yeah, that just upsamples the mesh.
Yeah. So that's what you have to do if you have like 10T data and the voxels get like to 0.2 or whatever your guy's getting. So then your mesh from 0.75 is just too sparse, and then you basically miss some voxels. So.
But yeah, you need to iterate the inflation more because that's how they identify topological.
Yeah, so that was the sphere part. So we are basically inflating it and it becomes a sphere, and if you don't inflate enough, then this defect correction will work.
But yeah, so like HCP, what they used to do is they would upsample the surfaces using something like this mesh subdivide, and then they would kind of do a separate deformation step of these high resolution surfaces to the sub-linear integration. That worked okay. I think we stuck some comparisons of this approach into the analysis paper. It also works pretty well. Again, you just need more degrees of freedom in the mesh so that you can sort of form it to the high resolution figures like on high class. Actually, I think it's, yeah, so it's great to, yes, we sometimes include the T2 weighted
Like,
context.
not as an additional bunch, like running like Freesurfer.
In addition, yeah, because it's like the T2s, you see less dura, you see less tissue from the sinuses, and so it's pretty cool. There's like a T2 peel flag or something.
Yeah, but you cannot just run it on the T2.
Right,
It's a second, yeah, so it's not gonna work if you just run it on the T2.
Only T2.
Oh, yeah.
Yeah,
You
that's
still need
no-
an MP
that's a
range,
no.
but in addition to the MP range, you can add the T2. That's pretty clever, because what it does then is it positions the
Yeah.
surfaces in such a way that respects the gray CSF work in both that jointly within the MP range and the T2 space, which is pretty cool. Yeah, and so it still generates the lateral surface in the exact same way based on the T1 alone, but the peel surface placement takes both of these into account.
Is that something that is collected by the MENP range sequence? Or
Unfortunately not, yes, the memory range is multi-echo, so multiple, kind of grading echoes.
Yeah.
And generally they're like pretty short echo times, because otherwise you get kind of shine through, the T2 star contrast and T1 contrast kind of fight. So generally you're not going to do TEs longer than that.
So separate acquisition.
It's a separate acquisition, usually a T2 space or T2 space flare.
Yeah.
It's kind of hard, to actually get them to be distortion matched, blurring matched. But yeah, with a little bit of effort, you can get a distortion matched T2. It takes another 8 minutes, though. That's the problem. It's like you get 6 minute MP range, 8 minute T2 space.
Right.
17, sometimes doesn't look great. Maybe it's whatever you want plus 17. So there's some challenges, but it's like 3 tiers.
So actually, and I'll let last talk, but we've run Freesurfer directly on a T2 of the weighted stuff.
But it was not Reconol though, it was Reconol clinical. The function was
yeah.
called. I don't know if that's on add-on or something.
Yeah, that's right. They have this new, what's his name? Yeah, it's got this new Freesurfer version that works on
Right.
kind of different contrasts. Some places that works. We've tried to kind of, we forced EPIs into Reconol.
Right.
Kind of looks okay, if you kind of prep the intensities
Right.
correctly. Yeah, I think we've had a lot of kind of forcing lots of data through the kernel.
Yeah.
Different fields of success.
It worked very well.
Yeah.
But I only tried it on one brain so far.
Okay, yeah, we haven't tried it.
Flag inspired with the Monday Oct GFE with structural functions. We run all of that.
Cool.
That's all.
On the high-risk flag, there's also this thing called decimation that Freesurfer does. I think they set a minimum mesh, mosaic area, face area, and I think if it's smaller than that, you go for a smaller mesh. So on the code it said that there's something called do decimation where you set like a minimum face area for the mesh, and if it's smaller than that, you come back to merge those faces.
Oh, yeah, that's
mesh. I think also you kind of avoid going to very small meshes to mitigate the sampling bias.
Sure, like, yes, it would make it simplified, but sure, why they do it. Because I think that generally they're not so interested in, the primary kind of goal of the kind of recons necessarily simplified, surfaces for fMRI analysis. But yeah, it seems that you generally don't want such a huge range of triangle pairs.
You said you're not smoothing, right? Like you prefer not to smooth?
For laminar kind of analysis, yeah.
But for Mate, like I don't have experience with high resolution, but for Mate, I saw like, I think previous lectures, like sometimes you don't really see the separate layer effects in terms of activation without smoothing.
Yeah,
So
I mean, I
you
could.
just see.
Yeah, I mean, I could smooth to see if there is anything there to basically help visualization, but for actual analysis, if I'm gonna quantify this activation, I wouldn't. It's gonna be noisy, but this is just the price to pay for small voxels.
And maybe I can comment, yeah, so exactly. So it's, if you're looking at like a 2D image and you want to visualize the activation pattern, sometimes smoothing is helpful. But if you think about it, most studies generate these kind of laminar profiles, right? You kind of average your data within your ROI, as a function of, cortical depth, plot as a function of cortical depth. And that's kind of a form of smoothing, right? You're averaging all of your data within an ROI, again, across different cortical depth images. So that's a form of smoothing, right? And that helps to increase, SNR by kind of canceling noise. And so it's not, it's averaging. But again, generally, whenever you see these profiles, that's usually the result of pooling data across, many different cortical.
Yeah, I guess so. That's the kind of smoothing that I do use.
Yeah.
And also like several subjects or a single subject, like when you say this kind of like.
Both. So if you think about it, if you are going to smooth, thin layers and then generate, this cortical depth profile, it's a bit redundant. It's like, again, the smoothing is helpful to visualize, but then if you're just going to average across your whole ROI anyway to generate the cortical depth profile, the smoothing, especially if you smooth within layers, you're defined in the same way that you're defining your cortical depth profile. It's kind of redundant. That's why I was saying, David Norris on a paper showing that even at 1.5 Tesla, you could actually see like pretty decent, laminar activation. Even though there's really low SNR, it's because you had a nice big ROI in that case, and you could kind of average, pool data across, in this case, big ROI because his activation was simple, but he was able to kind of average across this large ROI and still generate a pretty reasonable cortical depth.
So you mentioned that these DNN-based tools for skull stripping, for segmentation, they do a typically better job at such things. But the training data was all at 3T, or was there 7T data in the training data?
I don't think there was 7T data included. I think there are different types of data because they're supposed to be like working on N images. I honestly don't know the details of how they work, but they're supposed to work well in like the traditionally expected in Freesurfer processing data. We haven't tested them on the sub-millimeter data, and it seems like previously, maybe the Freesurfer wasn't like necessarily optimized for the kind of data we use. So I'm just, I want to test it before I use it.
So these tools that are, these DNN-based tools are now integrated within the 8.1 stream?
Yes.
Yeah.
And 8.0 as well.
Okay. Yeah.